Hey guys, welcome back to Consistent Code. So today's problem of the day is power of 2 and subsequences. So the question is that we are given an array A of size n. Now we need to return the number of non-empty subsequences such that the product of all numbers in the subsequence is power of 2. And we need to return the answer in modulo 10 to the power 9 plus 7. Now what does that mean? Suppose that n is 3 and if my array contains 1, 6 and 2, so I need to find all those elements. I need to find the number of subsequences such that the product of all the numbers is in that subsequence is power of 2. Now think of this like we want uh, the numbers such that suppose I'm picking some numbers from this any array. Suppose I'm picking A, B, C, D, E. Let them be any numbers, and what I want that their product should be A into B into C into D into E. So what I want that their product should be a power of 2. Now how is that possible? We There's one way to know that it will be a power of 2 only if A, B, C, D, E are all powers of 2. Why is that so? Because you can observe, suppose I'm having 2, 1, 4, then 8, then 12, sorry, not 12, 16, 32. Now, what are these? And this is 2 to the power, no, let me just write power of 2. So I will be just writing the power of 2. So 2 is 2 to the power 1, 1 is 2 to the power 0, 4 is 2 to the power 2, 8 is 2 to the power 3, 16 is 2 to the power 4, and 32 is 2 to the power 5. So what can you observe from this? If I want that the product of all the numbers is a power of 2, and when I need a power of 2, then I should multiply. If From this you can observe, if I'm having any number like 2 to the power a, and if I multiply this number with another number 2 to the power b, then I will get 2 to the power a plus b. So what does that mean? If two numbers are by themselves the power of 2, and if I'm multiplying them, then I will always get a number which is a power of 2. So if I want the product of all the numbers, I have to choose the numbers from this given array such that their product is a power of 2. Then the numbers which I should choose should also be powers of 2. So what is our conclusion? That the numbers we need to choose from given array should all be powers of 2. So this becomes our conclusion. So how now the problem is, now we have simplified the problem. Now we need to choose the numbers which are powers of 2, right? So how can we do that? Now how to uh, know if a number is power of 2? Let's say if I just consider this example of 1, 6 and 2, how can I know that 1 is a power of 2? How can I know that 6 is a power of 2? And how can I know that 2 is a power of 2? Well, now just see one thing. What is the binary expression for 1? It's 0, 0, 1. Similarly, just check out the binary expression for 6, and that's 1, 1, 0. And similarly, just check out the binary expression for 0, the 2, that's 0, 1, 0. So what do you observe? We know that 1 is a power of 2, 2 to the power 0 is 1, and we know that 2 to the power 1 is 2 itself, and 6 is not a power of 2. So in now just check their binary expression. In 1 we can see that there's only one set bit. In 6 we can see there are more than one set bit, and in 2 we can again see that there is only one set bit. Hence, can you deduce one thing? All the powers of 2 will always have only and only one set bit. So this is what you can deduce from this. This is what you can find from this observation. For example, let's see. If I just see 2, its binary expression is 0, 1, 0. If I see 4, its binary expression is 1, 0, 0. If I see 8, its binary expression is 1, 0, 0, 0. If I see 16, its binary expression is 1, 0, 0, 0, 0. So in all of the powers of 2, there will always be only one set bit, right? So with this observation, so this was first we simplified the problem into that we need to choose only those number in which in the from the given array which are power of 2. Now we have also simplified this into a smaller problem, that if we want those number which are power of 2, then though the numbers which are power of 2 will always have only and only one set bit. Now how to find the number which is having one set bit? So one approach can be that you can just right shift a number. Suppose a number is number, then you can just right shift it with 1 and count the number of set bits. But in this method, you will have time complexity. I mean, you will get time complexity very high for this method. So you will get EL. So how to do this efficiently? For that, we can use an algorithm. And what is that algorithm? So efficient algorithm would be that you suppose you have a num. So what you can do, you can just say that while the number is greater than 0, you can say num should be, and you should take an AND operator of the number with number -1. This is a bit manipulation algorithm, which is a prerequisite, which you should know. This efficient algorithm, this is a prerequisite, and you should know this algorithm. You should learn this first, and if you don't know, I'm telling you what this algorithm is. That to find the number of set bits, to find the number of set bits in a number, and here you can just create a count variable which should initially be 0. This count variable will you know store the number of set bits in the number, right? So while you can perform this operation, you can say that you have one more set bit in that number, and this is the efficient algorithm for calculating the number of set bits in a number, which you should know. So this is how we can solve this problem. So now, in this given array 1, 6, and 2, we needed to find those numbers which are power of 2, and the number which are power of 2 will always have only one set bit. Now we can again just find those numbers which have one set bit using this efficient algorithm. And um, let me just comment out all this part. So this using this efficient algorithm, we will be finding the count of set bit in a number. And once, if the count will be 1, then we can say that this is a means this number is a power of 2, because the count of set bits is 1. And let us say that uh, int n equals to 0. And what will this n store the number of uh, elements in a having uh, which are power of 2. So this n should store that. And if count is 1, then what I can say, that we can increment this n, right? So this becomes my efficient algorithm. And I need to check for all the elements in this array. So I need to do this process of counting the number uh, after this line. So I can uh, use this efficient algorithm here in this for loop. So here I will create a for loop for int I equals to 0, I less than n, that is the number of elements in the array. Now in this, so I'm doing this efficient algorithm for every element in the array, right? So now we have the count of numbers which are a power of 2. Great. So once we have a count of number which are a power of 2, and we need to find the number of subsets, or the number of subsets which we can generate using the given number of sets, then we know that that will be 2 to the power n and minus 1, and this will be our answer. So we need to return this. So how can we do that? One thing which we can do is we can just create a for loop from it I equals to 0 to I less than n I plus plus, and we can say that answer, initially I can say that answer is 1, and then I can say that answer should be multiplied by 2, and after that I can return answer minus 1. So this is one approach, but this will again give me a T and E because it will take higher time complexity. So how to solve this problem? To solve this problem, I will use modular exponentiation. This is another prerequisite which you should know. This, because if I will be using this algorithm to calculate the power of 2 to the power n, then that will be having time complexity of big O of n. But when I use this modular exponentiation, I have the time complexity of big O of log n. So I will just use this modular exponentiation algorithm. So I can create a, I can just return my answer as fast power of 2 to the power n minus 1 and plus this m. Let me just define this m because we need to take the mod. So I will take const int m as 29 plus 7. So that will be our modulo m. Uh, so and we just need to return the mod of it modulo m. Now I just need to define this function fast power. That is the modular exponentiation, which will give me the fast 2 to the power n in o n log n m complexity. So let me just do that. So I will just create a function long fast power that will take the first argument as the base. We will be calculating a to the power n using this function, and the second argument as n, that will be the power. So I'll just mark my result as 1 initially. Then I can just say while my power I'm calculating using this, I'm calculating to calculate a raised to power n or a to the power n, right? So to calculate that, I want my power should be greater than 0. Until my power is greater than 0, what I will do, I will first check if the power is odd. If the power is odd, what I will do, I will just say that result should be result into the base and then mod m, and in each step, otherwise what I will be doing, I will be multiplying base by itself. I will be taking the mod and I will be dividing the power by 2. So that's what I will be doing, and then I will be returning my result like this. So once I'm done with this, this fast power function should give me the power of 2 a to the power n in o log n time. So this will make our solution very efficient. So I will just again repeat what we did. First we calculated all the numbers which from the array, which are the count of numbers which are a power of 2 in the array. So and then for calculate to check if a number is power of 2, we observe that all those numbers have only one set bit. Then we use this efficient algorithm to count the numbers which have only one set bit. Then we got the count of those numbers in this n variable, and then we simply return 2 to the power n minus 1 as our answer. And to calculate this 2 to the power n in O log n time, we used modular exponentiation. So the prerequisites for this solution were this efficient algorithm to find the number of set bits in a number, and the second prerequisite is this modular exponentiation. But if even if you don't know, I hope you were able to get it. I also explained how to do both of these algorithms, and now let's try compiling and running our code. So there's an error. Okay, while num is greater than 0. So I have not defined this num. What is this num? This is basically the element of array, right? And so here also I need to do it a of I, and here also a of I minus 1, right? So now let me just try running this again. So I'm getting the correct output which is expected. Let me use example test cases also. So I'm getting the correct output. Now let's submit this code. And so we have solved the problem successfully. I hope you liked the explanation, and if you did so, make sure you hit the like button and subscribe to the channel, and I will see you tomorrow in the next problem of the day.